The light that our eyes can see, which we call visible light, is only one small portion of what we call the electromagnetic spectrum, which extends from short wavelength gamma rays at one end to long wavelength radio waves at the other. In this video, we'll explore basic properties of this complete spectrum of light. You are probably familiar with the idea that white light is a mix of all the colors of the rainbow, as you can see when we pass white light through a prism. The rainbows we see in the sky occur for the same basic reason. Water droplets in the atmosphere can act like miniature prisms, showing that white sunlight is actually a mix of all the colors of the rainbow. Although our eyes can see only the colors of the rainbow, there are other forms of light. For example, in 1800, the astronomer William Herschel, better known for discovering the planet Uranus, noticed effects that he recognized as being due to light from beyond the red end of the rainbow. We refer to this light as infrared light. In a similar way, we refer to the light that lies just beyond the blue or violet end of the rainbow as ultraviolet light. The idea that there are forms of light that our eyes cannot see will make more sense if we briefly explore the nature of light. You've probably heard that light is a wave, which is something that can transmit energy without carrying material along with it. For example, tossing a pebble into a pond generates waves that carry energy outward, but if you watch a floating leaf, you'll see that the water itself is primarily moving up and down. Light differs from waves on a pond and other familiar waves because we cannot see anything moving up and down as it travels. However, we can tell that light is a wave from its effects on matter. For example, if you could set up a row of electrons, they would bob up and down as light passed by, demonstrating that light waves carry a vibrating electric field. Light also carries a magnetic field, which is why we say that light is an electromagnetic wave. Let's focus on the traveling wave. The distance from one peak to the next is called the wavelength. The frequency is the rate at which the wave vibrates up and down, which is equivalent to the number of peaks that pass by a point each second. Putting these ideas together, we find that the product wavelength times frequency must be the speed of the wave. In the case of light, the speed is always the same in empty space. We use the letter c to represent the speed of light, which is 300,000 kilometers per second. This leads to a very important idea for light. Because all forms of light travel at the same speed, light waves with longer wavelength must have a lower frequency, and those with shorter wavelength must have a higher frequency. We'll use this idea as we return to the complete electromagnetic spectrum. Visible light represents wavelengths from about 400 nanometers on the blue end to about 700 nanometers on the red end. As we've discussed, infrared light comes beyond the red end of the rainbow and therefore has longer wavelengths than red light. Ultraviolet lies beyond the blue end and therefore has shorter wavelengths than blue light. For convenience, scientists further subdivide the regions beyond visible light. On the long wavelength end, radio waves represent light with wavelengths longer than infrared. On the other end, we define X-rays to have shorter wavelengths than ultraviolet, and gamma rays to have the shortest wavelengths of all. This scale shows the wavelengths of the different forms of light in meters, and these diagrams show familiar objects of various sizes for reference. Notice that the wavelengths span an enormous range, with visible light representing only a narrow band in the middle. Also notice that scientists sometimes refer to the region near the border of infrared and radio waves as microwaves, and astronomers sometimes further divide this region into bands they call millimeter and submillimeter waves. Now consider this question. Which form of light has the highest frequency? Is it gamma rays, X-rays, radio waves, or microwaves? The answer is A, gamma rays. Remember that light with shorter wavelength has higher frequency. Therefore, the fact that gamma rays have the shortest wavelengths means they must have the highest frequencies. Here, we've added a scale to show the frequencies of the different forms of light in hertz, which means waves or cycles per second. You can check for yourself that if you multiply the wavelength of any form of light by its frequency, the result will always be the speed of light. So far we have been discussing light as a wave, but you may also know that, like particles, light comes in pieces that we call photons. Individual photons carry energy, and the energy of a photon depends on its frequency. This scale shows photon energies. For our purposes, you can ignore the units, but notice that as you should expect, gamma ray photons have the highest energy because they have the highest frequency, while radio photons have the lowest energy because they have the lowest frequency. The many forms of light play important roles in our daily lives. For example, radio waves carry so little energy that they have no noticeable effect on our bodies, but they can make electrons move up and down in an antenna, which is why they are so useful for communication. Moderately warm objects emit infrared light, which is why infrared cameras allow us to see people and animals in the dark. And X-rays have enough energy to penetrate living tissue, making them useful for medical imaging. The entire spectrum is also crucial in astronomy because we receive light of all types from various cosmic sources. The different wavelengths of light teach us different things about these sources, and only by studying light from across the electromagnetic spectrum can we get a full picture of the objects we study in astronomy.